We've heard a lot about fire on the east side, and certainly when I moved out here in 2010, it was all about fire on the east side. And there's been a couple big fires on the west side, and sort of perspectives are changing. We're learning a lot about it. And what was once really characterized as really sort of a long return interval, high severity fire regime on all the moist forests of Oregon and Washington, that idea has really been being revisited recently, and we're learning that these fire regimes, the historic ones, are really far more complex than that. And so I wanted to start with just a little look. This is just a map of Oregon and Washington, and it's a fire suitability map. And what it is a statistical model. The blue means low, the reds and the yellow means high. And it's basically a model of where we might expect to see fires given specific climate conditions. And the first thing to me that pops out automatically is this really distinctive geographic line, right, that goes right down the crest of the Cascades and then sweeps across southern Oregon, and all this blue, right? And there's really no recent fire perimeters in there. And the first question that I think we have to start asking is why is that? What is different about the western part of the region than the eastern part of the region? And to start with that, we need to start thinking about how some of the factors that limit fire and fire activity vary geographically. And so the first thing, to have a fire, of course, you need ignition. You need some sort of spark to get that fire going. And here I have a map. I think this is from 1993 to 2013. And these are all the fire starts across the region. And so our first explanation, potentially, for why we haven't seen much fire is really the lack of ignition. And this figure here includes lightning and anthropogenic ignition, so human-started fires. But as you come across, there's really not as much lightning, right? Up towards the north in Washington on that west side, and as you come down to the south, and then as you get towards the Crescent in southwest Oregon, we get more lightning. And so ignition is really, really limiting. The second thing to think about is really this regional bioclimatic setting, right? The Pacific Northwest is really a very diverse region. And the three main factors that we want to think about for fire, and this varies where you are in the region, and so as you start thinking about where you work, where you operate, where your land is, this is a great place to start. Things like summer temperature, right? Even within Western Oregon, we have these huge gradients where it's much, much cooler towards the coast, and then as you get into the valley, it gets much, much warmer, and then as you go up in the Cascades, it gets cooler. Summer precipitation varies as well, too. Down the crest of the Cascades there, once you get below the Mackenzie River, there's far less summer precipitation, and summer drought is much higher. And so these are some of the major factors biophysically across the region that you want to think about when you start thinking about fire in your neck of the woods. And when we put all this together, we've come up basically with this map of pre-settlement fire regimes. And what we have here is we've sort of divided them into 4 different fire regimes. Usually people talk about 3. The first is this infrequent high severity fire regime. Really, really, really long intervals between fires, hundreds of years. 200 years, 300 years. And this regime historically dominated really basically from the Olympic Peninsula down through the Coast Range in the dark blue, as well as up in the Washington Cascades, and then down into the Oregon Cascades. And then what you can see here is these burned areas with the hashes. These are old fire perimeters from, I think, Plummer in the early 1900s went out and mapped these. Once you get into that middle area of the Cascades, there's this change, and it's a little tough to see here, but we get into this sort of light blue, what we call moderately frequent mixed severity. And this is sort of what we're really starting to think about now in this southern part of Oregon, and moving away from that standard placing fire regime. And then as you get further south into southwest Oregon, yellow, we have this frequent mixed severity regime, and then also this very, very frequent low severity regime. And so we have this relationship, right, between frequency, how often we have fire, and then the general severity or overall fire effects. And one way to characterize these is with some of these figures. And what I have here, this is, I think this is the most complex figure that I'm going to show everyone. So hopefully that's good at this point in the afternoon. But I have these three generalized types of fire regimes, this low, this mixed, and this high. And then on the y-axis is the proportion of the total area burned in each of those severity classes. So how much tree mortality. And so our really stereotypical fire regime for the low severity is these eastside ponderosa pine forests, right? Historically, we might have had fire every 5 to 20 years, and they maintained these really open, low-density forests dominated by big overstory, very fire-tolerant trees. As you move to the other end, to the high severity, you can see that red there. Most of the area burned is burned at high severity, characterized by lots and lots of tree mortality. Maybe there's some unburned little refugia from that fire mixed in there, but most of the area by and by is really high severity. So we have these two bookends, and we find those kinds of regimes in really, really cold and wet places, right? When you start thinking about that summer drought, you may not get that every year in some of those cold and wet places. And so that's why frequencies are much, much longer in between. And then finally, we have what fire ecologists call in the middle is this mixed severity fire regime, where we really have elements of both the low and the high all sort of mixed together in this mosaic. And this is something we're learning a lot. There's a lot of discussion among fire ecologists about what this actually means, but it really does have elements of both that low severity regime and that high severity regime. And what we're learning is this western hemlock Douglas fir type that dominates most of the western part of our region. It really spans sort of portions of all these different regimes depending on where you are. And so it's really, really broad, and that's why that map is going to be really, really important. And so to dig in a little deeper to each of these regimes, I think this is probably the one most folks are familiar with from the east side, this frequent low severity. And so fire maybe every 5 to 25 years. It's more typical of those ponderosa pine-dominated forests in the east, but this is historically what would have characterized oak woodlands in the Willamette Valley. So that big white spot, the Willamette Valley keeps sort of getting left out here, but that probably would have been red, right? Really, really frequent fire from Native American burning. We know about these fire regimes because we have this rich history of fire scar studies, specifically from the east side. And so ponderosa pine does a really, really good job of recording frequent fire. A fire will go through and wound a tree, it'll open up a cat face, and then every other fire that comes through there will leave a record in that scar. And so people that study these, they go out there and they cut these cookies, they sand them down, and then they can date when each of those fires was, and these trees live potentially for 400 or 500 or 600 years, and so we can look really, really far back. So we have a really, really rich knowledge of that. And in terms of the limiting factors in this regime is mostly we find them in hot, dry places, right? And so the conditions for burning exist pretty much every year. So what limits them is either ignition or fuels. A lot of these places are much, much lower productivity. And so it might take 10 years for fuels to recover before you could carry fire through one of those systems again. We also know that we've been putting fires out, or this is just sort of a general conceptual model, an illustration from Bob Van Pelt, where at time one you have an unburned forest, a fire comes through. Basically in the middle there, it consumes the understory vegetation, the low fuels, creeps around the surface, kills some of the smaller trees, and then it sort of maintains that open overstory structure over time. And we know that we've been going through this long period of fire exclusion in many of these forests. I would argue all the forests of the Pacific Northwest. And what's happened is that we've had these long-term changes in density, right? There's far more trees, orders of magnitude more trees in many of those east side forests than were historically, and the composition has changed. Sort of the poster child for that is grand fir over on the east sides that's come in. And so here we have another picture from Bob Van Pelt where you have that frequent fire coming through, creating that structure in the second term, and then you put the fires out and you get all this accumulation of live and dead fuels. And ultimately, this has turned into this increased potential for what we call uncharacteristic fire behavior and effects. Right, and so that's what we're seeing in a lot of these fires today. I think cumulatively in all the ponderosa pine in the Pacific Northwest, about 25 or 30% of the area burned has been this high severity effect where all the trees are killed. And historically, we think it was about 4% and limited to these really, really, really small patches. So we're seeing these uncharacteristic effects. One of the big things is the losses of these old legacy trees, right? And so if you think about Oregon white oak and Douglas fir, you could see a very, very similar thing. If we move on to the mixed severity regime, this becomes far more important towards the south, where ignitions are more common, lightning is a little bit more common, and summer drought becomes far more prominent. And so this area is represented here by this lighter blue. And what you'll see, it's a little tough to see with that darker blue, is that those historical patches don't really occur very much in there. Right? And so we think fire was really, really frequent, except on the west side. We have a limited understanding of this, is what we're really figuring out. And Douglas fir does not fire scar like ponderosa pine. It will fire scar, but it grows over really quickly. And so those records are lost. What we're learning now is that this fire regime, particularly in that southern part of the Cascades, is far more complex and less well understood than we think historically. Some of the early work to start sort of unpacking that came out of the H.J. Andrews. This is some of the work of Morrison and Swanson, Fred Swanson, who was with the Forest Service for years, did a lot of this work. And what they would do is they would go to these stands in the H.J. Andrews and use the age structure of the trees and try and recreate fire severity patches from back in the 1700s and 1800s. And this is just a depiction of one of those. This area, there's a scale bar, 1 kilometer. This is about 5 kilometers by 5 kilometers. So there's some pretty big patches of high severity fire in there, potentially related to topography, things like that. But by and large, most of it is really low and moderate. And so you're leaving lots of overstory trees, what we call non-stand replacing fire. Throughout the years, I think Fred had multiple graduate students. He always referred to them as the Peters. There were these three. It was Peter Impara, Peter Teensma, and Peter Weisberg. And what those guys did was they went out to all the clear cuts in the 80s and 90s and were able to pull out some of those fire scars and start recreating a little bit more of a better understanding about those frequencies. And then on a much, much broader scale, this is a figure more recently that Tom Spees put together. And this has maybe back in the late 80s or early 90s when they were first doing the characterizations of old growth across the Pacific Northwest. Tom was taking observations on the percent of trees with fire scars, mostly Douglas fir, that had charred bark in these stands that they were sampling, right? And so if you go there and a tree has char in its bark, you obviously know it survived, right? The limitation is that you don't know when that fire was. And I think this illustration shows really, really clearly that as you go from south to north, there's this really distinctive biogeographic dividing line. Anything to the left of that, you can see 50, 60, 70% of those large fire-resistant trees had char in their bark. And then all of a sudden you get to the north and it disappears, right? And so we probably move into more of a stand replacing fire regime. And so we're learning a lot about this fire regime, this mixed severity fire regime these days, primarily because there's been a fair amount of fire out there. And what we know is that there's strong bottoms-up controls on fire severity and fire behavior. And when I use the word bottom-up, I mean things like fuels and topography. These things are very important. You can see in this landscape here from Southwest Oregon, there's that one big patch in the middle. You know, maybe the wind picked up and sort of blew through there. But a lot of the other areas are really, those patches of high severity coincide very well with ridges, steeper places, and things like that. And so forest structure and topography are really, really important. And then occasionally, we have these large patches of high severity fire when you get fires that are driven by things like wind. This is, I'm going to show you a bunch of these. This is some burn severity maps that I put together with Landsat imagery. Landsat is a satellite. It's been taking pictures of the Earth twice a month since 1984. Each of the pixels is about the size of a baseball diamond. And with some basic GIS skills, you get a pre-fire image, a post-fire one, you difference them, and then you make these maps. And these fires are primarily down, I think it's the Apple Fire, is that maybe that bigger one down there in the bottom left, and kind of that interface in the southern part of the Cascades between wet and dry forests with some western hemlock there in pink, and then some of the drier grand fir types. And what you can see is that fine and coarse scale mosaic, even in contemporary fires, right? So most of those patches are pretty small, and occasionally some of those fires up in the top, you get these big areas that are really, really blown out, probably little weather-driven portions of the fire. And so moving on to the last one, this infrequent high-severity regime, which is really what dominates most of Washington, and then most of the Coast Range, with the exception of the valley margins, and then a lot of that area north of the Mackenzie River to Mount Hood as well. And so it really covers a big part of our region, and a lot of sort of the breadbasket, right, of where people are going trees and Douglas fir. And this regime is really characterized by really, really long time periods between predominantly stand replacing fires. Like I said before, a couple hundred years, 200 years, 300 years. And most of our evidence for the pre-settlement ecological role of these fires, again, comes from age structure, right? If you're a fire and you roll through and you kill all the trees, you do not really leave any evidence of what was there before. And so what we do is we go in and we age trees and look for cohorts, right? If you're in a large patch, say a 100-hectare patch of forest, and they're all Douglas fir and they're all 200 years old, it's pretty strong evidence that there was a major disturbance that happened and these cohorts established. And so that's most of what we know about this fire regime. And it also, we know it exists primarily in these wetter or cooler forest types, where the climate isn't necessarily always suitable for a fire every year, but maybe every 50 or 100 years you have these really, really long extended droughts and one of these fires will blow up. Again, most of the Coast Range down on that western side, closer to the coast, and then a large portion of the Cascades. And here I wanted to point out sort of how this corresponds with those burned areas from the early 1900s. And in addition to those age structure studies, we have really a rich legacy of maps that some of the early foresters left us from the 1930s and the early 1900s, and some more that I'm going to show you. And they line up pretty well with this fire regime map that we made. You can see in the Oregon Coast Range, huge fires, right? In the 1800s, these things are still leaving a legacy on landscape structure and composition in the early 1900s. That big patch there over in the Cascades, just south of the Washington border, I think, is the Silverton Fire, 1860s, almost 1 million acres. 1 million acres is huge. That's the Yellowstone fires in 1988 were like 750,000. That is a huge fire. We've seen nothing like that really in the Pacific Northwest since then. The Biscuit Fire was about half of that size. And what these sort of disturbances, these fires create, is what we call a coarse scale mosaic. This is, these are contemporary fires. This is from the subalpine forest up in northern Washington. The Tripod Fire back in like the 2007, 2008. And so these fires, these are really the way we think they operated historically, right? We haven't really had much of a change in the fire regime in these sorts of places. And I think one of the neatest things, let's see, is this series of maps that Peter Teensma put together, basically using a combination of some of those old Gannett and Plummer maps, as well as some of the age structure data. And this is the northern part of the Oregon Coast Range. I've added Salem here. It apparently didn't make his maps originally. And what you can see is sort of a glimpse of where recent fires were, as well as the age structure that has been driven by these fires. In 1850, 1890, 1920, and then again in 1940. And so if you look at 1850, there's some huge patches, that sort of crimson maroon. Those are basically stand replacing patches of fire. This is the Nestucca Fire, the Siletz Fire, the Yaquina Fire. 1850s was a big period for fire in the Pacific Northwest. And then as we go on through the 1890 and 1920, we see a couple more fires. What we see sort of in the middle there is reburns, right? And so we talk about these long intervals between fires, but some of these places are prone to reburning as well. And so you might go 400 years without a fire, and then you might have 2 or 3 in a series of 20 years or so. And if you go to the 1940 map up to the north there, right next to Tillamook, that's really exactly what happened right there. I think the Tillamook fire started in like 1933, and then every 6 years, they had these huge fires again and again. And I think the first one was on the order of 300,000 acres. It's a really, really big fire. And so this is just to sort of demonstrate the size and the magnitude of what some of these fires can do in standard placing fire regimes. And we know from these maps that these sorts of situations, these events, are really the normal for those places that we've mapped as standard placing fire regimes. And so you have to think, what gives rise to these? How can we try and predict them? A lot of times we talk about these things as what we might refer to as a black swan event. It's like a stock market crash, these big events that have huge impacts, but we really have sort of a poor ability to predict when or where they're going to happen. And so there's really three major factors to think about when we start thinking about these really large standard placing events. And the first one is, of course, an ignition. Right? And on that west side and the Coast Range, a lot of these ignitions are humans. Native Americans back in the 1850s. Today, human ignition there's not a lot of lightning out there necessarily. The next thing is very, very dry late fall conditions. So these would be exceptional droughts, maybe a 50-year drought. And then the final thing, the real kicker, right? We can have these things happening, but the real kicker is what we call one of these dry east wind events. So one of these synoptic wind events that just comes up, crosses the crest of the Cascades, and once there's that ignition and the dry conditions, these things just blow up, right? And this is a figure from this guy Kramer in the 1950s went up to Portland to the airport and harvested all their wind and relative humidity data to try and look at the frequency of when these wind events would happen, right? And there's actually a pretty strong pattern here that we can pick out. And can't quite remember the thresholds he used for how fast the winds needed to be and what the relative humidities were. But this figure shows a very, very clear pattern that in the Pacific Northwest, there is a specific window of vulnerability to these events, right? May, June, July, when the dry season starts, these things almost never happen. But you hit late August, September, and October, and the probability that one of these is going to happen gets much, much higher, right? And so these black swan events, we can sort of narrow things down a little bit, right? He also did something that he called, this is the maximum number of days. That was the average number of days. And so sometimes you might have six of these a month, right? And so this threat is out there, and it's real. And as an example to show you sort of what this might look like, this is this really neat map that I dug up of the Tillamook daily fire spread. So this is that first, I think about 300,000 acre fire from the Tillamook burn. Probably you can't read the weather data there, but for that first approximately 10 days, wind speeds were down 5 to 10 miles an hour, 15 to 25. Relative humidity was up in the 40s. And then towards the end, that 25th and 26th, all of a sudden the wind shifted from the east, got up to 20, 35 miles an hour. Relative humidity dropped. And all of a sudden, I don't know, that's 75% of that 300,000 acres that burned in that one day, right? So you better get out of the way when one of those things is coming. And so we know we've essentially had no fire in the Coast Range these days. There's been a couple really, really small ones, but we've been able to put them out. And most of the activity in Oregon has been in the West Cascades, excluding, of course, southwestern Oregon. And what I have here is I've taken all those burn severity maps for the Western Cascades and put them together to look at temporal trends over time. And what we've learned is that there is a trend of increasing fire activity in the Western Cascades. But on average, let's see, these are in hectares, so if you multiply that times 2.5, there's not that much fire out there on an annual basis. A big fire year, 2003, that's about 25,000 acres. Of course, this is missing 2017, right? What happened in 2017, right? The Eagle Creek fire, right? And so that's all of a sudden one fire you burn, about a third of the area that's been burned in the last 30 years together. And so these things can change really, really quickly when you have systems that are driven by large events. And what I have here is a fire progression map from the Eagle Creek, and I wanted to just sort of point out these 2 days where there were, I believe there were east winds that they sort of spread from where it started in the middle up there. And you see that it went along the Columbia River to the east and then up into some of those higher elevations. And again, that's makes up a big part of the area burned in that fire. And then when we look at the burn severity map, it ends up that, let's see, only about 10 or 12% of that area burned with sort of a stand replacing effect, right? And when you look at that burn severity map, where you see the red areas, there's really still a strong effect of that bottom-up topography and fuels in a fire like this, right? And so think about the havoc that Eagle Creek fire, right? It's raining ash in Portland. Students going to Oregon State from the east side can't get there because the highway's closed. This is a 50,000 acre fire, right? And think about the potential of what a 300,000 acre fire would do on the west side, right? Yeah, so cumulatively, a lot of these fires on the west side are operating the way we think they did historically. These are just different vegetation types, and you can see that western hemlock. As we move up in elevation, we see a greater proportion of high severity fire, a lower proportion of low and moderate. Thinking to the future, Holly showed this figure as well. There's a number of different studies out there that project future fire activity, and they use all these different models. And they predict all these different attributes of fire, area burned, fire probability, things like that. And the results are a little bit all over the place, but they all consistently project that we're going to see more fire, right? And so if you think about 20,000 acres a year and a 400% increase, as far as the area that accounts for, it's not much of the region, but as far as the potential economic and social consequences, when you think about what the Eagle Creek did, it could really, really add up. And so some things to consider in the future. Patch size, how big are these high severity patches? Do you need to go in there and plant? Will seeds be able to disperse in there and regenerate? Seasonality of the fires, right? As our fire season gets longer, falls get drier, the fire season is longer, and there's just a greater probability of fire starts, potentially those east winds. Productivity, I really like this picture here. These are all regenerating stands from 20 years after a fire, right? And what's the difference? You see this one up in the Silver Fir zone where there's tons of regeneration, right? Very, very productive. On the bottom, this is the fire up near Waldo Lake 20 years later. Very, very little regeneration. Those cold, low productivity places, it takes a long time. This other one is from Southwest Oregon where there's resprouting hardwoods. Things come back very quickly. Along with post-fire climate, those are really what are going to drive what comes back after that fire. Some of the other things, invasive species are huge. And then these state changes where you basically, maybe you have a short interval burn and all your conifer generation gets wiped out in that second fire. So these are just some things to consider. And then I was going to sort of close with just a couple sort of broad strategies and things like that in terms of pre-fire management options. And you really need to think about where you are and what that historical fire regime was when you think about which options you might consider, because they vary among those fire regimes. And so, basic stand level fuel reduction, thinning, surface fuels, ladder fuels, low severity fire regimes, go for it, right? Those can really make a difference, especially under moderate weather conditions. As we get into the mixed severity regimes and the high severity regimes, probably all the thinning and fuel treatment in the world isn't going to stop a Tillamook fire, right? Those might not be effective. The question mark in the middle there for those mixed severity regimes is what happens after you go in and thin? Do the hardwoods come back even thicker than they were before? That's something I think we still have a lot to learn about. Consistent across other things, reduce other stressors, limit human ignitions, aggressive wildfire detection. Basically assess fire impacts relative to your management objectives, right? A low severity fire through the Willamette Valley could knock out some of those encroaching Douglas fir and leave your oaks, things like that. So take those effects and put them in terms of your objectives. Leverage natural regeneration. promote species and structural diversity within and across stands. We know that big old Douglas fir are very resistant to fire, and that small trees and plantations are very sensitive, right? So you can start thinking about how you can leverage variability in stand structure or heterogeneity to maybe hedge your bets in terms of what you have out there. Coordinate post-fire activities with adjacent landowners. In this fire in the west side, despite the sort of the history of it, we're really just starting to learn about these fires. And so use them as learning opportunities, monitoring trials, good opportunities for adaptive management. And with that, I'll take any questions.